Hello and welcome to this podcast where we'll be looking at electric field strength, part of the electric fields subtopic, part of topic 5, electricity and magnetism. We've already looked at charge, we've looked at the basics of electric field, and we've looked at Coulomb's law. Those are all prerequisites for this brief examination of electric field strength. The equations from the data booklet, the equation for Coulomb's law on the left there we'll be referring to, and the new one is the equation on the right. Electric field strength is what that symbol E is in that equation on the bottom right. It is not energy. This is a common confusion, so I want to highlight it right now. When you're dealing with this topic, E here stands for electric field strength. This is the definition of electric field strength. Please take a moment to read it. Remember, I said something about difficult to read writing sticks in the mind. Force per unit charge. That's the important part. The electric field strength is when you take a charged object and put it in an electrical field, what force will that charged object experience? And it depends on the electric field strength, how strong the electric field is at that point, and it depends on the charge on your charged object. So electric field strength is F divided by Q, the force per unit charge. Rearranging that, obviously, F equals EQ. The force will be the electric field strength multiplied by the charge on your object. The units of electric field strength are newtons per coulomb, and it is a vector quantity. The equations at the bottom show us how we can calculate this for a point near a circular, spherical point charge, where F equals KQ on Q2 over R squared is Coulomb's law. We know that E, electric field strength, equals F divided by Q. Therefore, the electric field strength can be calculated by KQ over R squared. So, near a spherical or point charge, to find the electric field strength, you have Q, the charge that's creating the electric field you're interested in. R squared is where the point in the field is that you're interested in, distance away from that charge, and K is Coulomb's constant. For example, what is the electric field strength 20 centimeters from a 50 millicoulomb point charge? Equation, electric field strength equals KQ over R squared. K is Coulomb's constant, Q is 50 times 10 to the minus 3 coulombs, and R equals 0.2 meters. Remember that we have to keep things consistent in terms of our units, so if we're using K in Newton meter squared per coulomb squared, we need everything in coulombs and meters to give us an answer in newtons. Plug in the numbers, do the calculations, you get 11.2 times 10 to the 9 newtons per coulomb. That's a pretty big number, which is a reminder that when we're dealing with electrostatics, when we're dealing with point charges, coulombs are a pretty big unit. Millicoulombs are a pretty big unit. Microcoulombs are actually pretty large. Nanocoulombs, picocoulombs, those are more commonly encountered when you're dealing with electrostatics. The electric field strength in a uniform field is a bit more difficult to calculate what it is at this stage in the course. What we just need to focus on is that it still has the same definition, it's still newtons per coulomb, but notice how it is constant. Since the electric field strength on a diagram, on a circuit diagram, not a circuit diagram, on a field diagram like this, I said earlier in a previous slide lecture that this diagrams the density of the lines is proportional to the electric field strength. And between two plates, you have a uniform field, uniform density of the field lines. Therefore, the electric field strength, newtons per coulomb, is the same anywhere between those plates. That does not necessarily apply at the ends where we have the end effect, but in the centers between the plates, it does apply. It's a vector, as I mentioned earlier, so let's just do another couple of questions here. We've got two identical charges. They're negative for what that's worth. And we have to calculate the electrical field strength for A and the electrical field strength for B. So at B, we have E1, which is caused by the charge on the left, and E2, the charge on the right. At A, E3, caused by the charge on the left, and E4, caused by the charge on the right. If we calculate the electric field strength at those points, then we should, in the case of A, just be able to use simple subtraction, B, vector addition, a little bit more difficult, in order to calculate the overall electric field values. So the resultant field strength at A will be over towards the left because it's closer to the left, and in B it'll be kind of mostly pointing down, the combined effect of both charges, but also pointing a little bit to the left. And we can do the calculations. Let's just do it here for the cases where they're in a line. EB, EA is the electric field strength due to the charge at A and due to the charge at B, which is positive charges, as you can see in this diagram. Standard equation that we've been talking about. Plug in the numbers. We've used 9 rather than 8.99. It doesn't really make much of a difference in total. And you get values here for EB and EA. And since they're in a line, we can simply subtract the small one from the large one to give us the magnitude and use our common sense to work out what the direction is. Please go through that again more slowly if you need. But that concludes this video presentation. Thank you very much.